This is problem 127 from chapter 12. It's a fun little problem where we have a train engine with a speed of 20 meters per second and it's going in the direction shown, and an acceleration of 14 meters per second squared, but the acceleration is going in the direction shown here, which is not directly towards the center of the curve. This is at an angle of 75 degrees. We want to determine the rate of increase in the train speed. Remember that the rate of increase is not necessarily the same as the acceleration. So the rate of increase is v dot, which is the tangential component of the acceleration. And we also want to find the radius of curvature. Now, in order to do this, we're going to take the acceleration that they gave us and we're going to break it down into normal and tangential components. And remember, the tangential direction is the direction that the object is moving in, which has to be tangent to the path. And the normal direction is pointing in towards the center of the curve. So, my goal first is to find the tangential and the normal components, and if you look in the textbook, they write the acceleration vector a different way, so this is one way of writing that. So it's the tangential component in the tangential direction plus the normal component in the normal direction. I kind of forgot what I was doing when I wrote it, so that's supposed to be the normal component. That's equal to v dot in the tangential direction plus v squared over rho in the normal direction. So the tangential component is v dot and the normal component is v squared over rho. I'd like you to be able to see that just by looking at the equation here. So this is being multiplied by the unit vector in the tangential direction. That makes it the tangential component. This is being multiplied by the unit vector in the normal direction. That makes it the normal component of the acceleration. Okay, they write this out in like 2 or 3 equations in the textbook, but basically you should be able to see that just from looking at the equation. So we're not going to think too hard about this, okay? So we have the magnitude of the vector and we have the angle of the vector, and I also know that this is the normal direction and this is the tangent. That should be a 90-degree angle there. It doesn't really look like it, but that's the normal direction. So, I mean, it looks kind of funny drawing it like this, but anyways, if this angle is 75 degrees and I know the vector is 14 meters per second squared, I can break that down in these 2 components. I could draw a right triangle. I could take this and move it over here. So this is the tangential component and this is the normal component. It is a right triangle. If you want to like rotate it like this, maybe that makes it easier to see. Okay, so this is a 75-degree angle, so the cosine component is the tangential component. This is equal to the hypotenuse, which is 14, times cosine of 75 degrees. It's a right triangle, and this is the opposite side. I don't know what I said for that. That's the adjacent side, so that's cosine, and then this is sine of 75 degrees. Okay, so we have the tangential component is 3.623 meters per second squared, and the tangential component is just v dot. So that's one thing we are looking for, meters per second squared, okay. And then this is 13.52, that's equal to v squared over rho. So, let's take that and solve it for rho. So rho is equal to v squared divided by the normal component. At this instant in time, v is equal to 20. So this is 20 squared divided by the 13.52, which is 29.59. It has units of length, so that would make that meters. And that concludes problem 127. So really what I wanted you to learn from looking at this problem is it's not always just taking the formulas that you're given and plugging numbers in. Sometimes we have to look at the direction of the vector and use the angle to break things down into components, which wasn't really that hard.